Hello everyone. Today is the 47th day of Leetcode 75 challenge. Let's begin with the 47th question. Question 1926, nearest exit from entrance in maze. The level of the problem is medium. I will request you to read the question beforehand and as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given a 2D grid maze representing a maze of size m cross n. Okay, let this be the maze of m cross n size. Each cell in the maze can either be an empty space denoted by a dot, which means you can move through it, or a wall denoted by a plus. You cannot pass through it. Fine. So plus are basically the blockers and dots are basically the way to move around. Okay. So basically the grid is of this kind. You are also given an entrance represented as entrance row comma column. So we have already been given the entrance dimensions, row and columns, which tells you the coordinates in the maze where you have to start. Okay. Suppose this could be the starting point. Fine. You can move into four directions: up, down, left, and right. Each move takes one step. So basically, if you move one step left, it will count as one of the step. Fine. Your goal is to find the shortest path in from entrance to the nearest exit. Okay. Suppose this is the exit here. So you have to find the nearest entrance or the nearest exit from the given entrance. Okay. Or the shortest distance. An exit is any empty cell located at the border of the maze, which could be first row, first column, or last column. First row, last row, first column, and the last column, right? This could be the exits. The entrance does not count as an exit, okay? Just keep that in mind, even if it is on the border. If there is at least one path to an exit, return the minimum number of steps required to reach it. If there is no path, return just exit and return -1. That's the question. The question is pretty simple. You are standing in a scramble basically, and this is your entrance, and you cannot claim entrance as your exit, even if it is in the last row, last column, first column. Okay, and you have to find the minimum steps required to reach the nearest exit. That's all. If there is no exit, you have to just return -1 in that case. Question is pretty straight and simple. The constraints are the length of the maze would be m, and the length of the row basically could be m, and the column will be n. M and N will be from 1 to 100, not more than that. And maze ij is either a dot or a plus. Entrance dot length will be equals to 2 because it will be 2 comma 3 or 4 comma 5, whatever, right? That's why. And entrance row could be from 0 to m, and entrance column could be from 0 to n. Okay, that makes sense. Entrance will always be an empty cell with digits. Fine. So I hope you understood the problem explanation and constraints. Now let's move to the next slides. Now let's understand the input output explanation. So let's take this grid, and this is the path where you can go, and plus this is a blocker basically, right? Entrance is 0 comma 0, so this is 0 0 1, right? Entrance is this one, right? So you cannot claim entrance as the exit, and you cannot go in this direction because plus is a blocker, or it is a wall basically, right? And there are not any more exits to it, therefore we return -1 as the output. Now let's take this example. Great. So it is plus 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 dot 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 plus plus plus, right? 0 1 2 0 1 2, and the entrance is at 1 comma 0 1 comma 0. The entrance is here. Okay, so if you could see, you cannot move up or down, right? You could only move straight because these are the blockers or the walls, you could say, and this is the only path. Therefore, to reach at this last column or the exit, nearest exit, we will need two steps: one step to come here and second step to come here, right? Therefore the output for this particular input is 2. So I hope you understood the input output explanation. It is pretty straightforward and simple. Now let's move to the next slide. Before going to the further slides, let's understand what is breadth first search in graph. Okay, a BFS is a graph traversal algorithm that explores all the neighbors nodes at the current level before moving on to the nodes at the next level. So it is same as the level of the traversal of BFS in the tree. Okay, suppose this is a graph given to you. If this is the source, okay, and let's start. Okay, so this becomes level 1. This will be what? Level 2 for this source. Fine. and this will be level 3, and this will be level 4. If you take this as this source node, fine. If you have taken this as the source node, then the graph would have changed, and this one and this one would have been the level 1. This one and this one would have been the level 2, and this might have been the level 3. So I hope you understood how we count or check for the labels in a graph. Okay. Now let's understand how we do that. So we just start from a source node, okay, and we mark it as visited. We enqueue into a queue because we are using a BFS. So we use a queue in this part. Suppose let this be the source node here, okay, and let it be 1, 2. I'm just writing random values, okay. Source is here, and since the queue is not empty, or while the queue is not empty, what we will do? We will pop this, fine. We will dequeue the front node. Now, after dequeue, you could do one thing. You could just put it in some list or something. Let me put it here, okay. Now we could visit all the unvisited neighbors of this particular source node, which are 1 and 2 in this case. So we put it 1 and 2, this is out, and we mark them as visited. Let this be this sign, let this sign cross sign be a visited one. Okay, fine. Now after that, you pop this one, pop, right? For the pop, you could see 3 is the level 3 node, you could say, right? So we'll push 3 here, and as the source node is already visited, fine. So then you come to 2. So you pop 2, you put it in the list somewhere, and you check, okay, source is already done, so you cannot do that. So what you do, you take 4, right? So this is was the level 0, this was the level 1, this was the level 2. Similarly for 3 or 4, for 3 you will pop 3, then you will pop, when you will pop 3, you will put 5, this will become level 3. And when you will pop 4, you won't be able to push 5 because it is already visited, and at the end you will pop 5, and that's all. So this is how level wise we do the BFS calls, right? So this is the way we do the BFS call, okay. And BFS is a FIFO to keep the track of the nodes to visit next. So since you are using Q use the concept of FIFO. Now why is it efficient? Because time complexity is V plus E, where V is the vertices, E is the edges. Each node and edge is visited once, right? We have just seen it. And space complexity is OV, which is the number of visited array, and queue, right? So you will have a queue which maximum size could be the length of a particular level, or the number of nodes in a particular level. Fine. In this case, the length would be 2. Okay. And secondly, the array. Okay. The visit array would be of length 1, 2, 3, 4, 5, or whatever the length of the nodes are there, which is V basically. Fine. Okay. Now, why it is efficient for finding the shortest path in the unweighted graph, level order traversal, cycle detection in undirected graph, connectivity checks in graph. So these are the way where you can directly implement BFS if you have the hint that okay, these are the concept of the question. Now, where BFS is used, okay, shortest path in unweighted graph. BFS guarantees the shortest path from source to the reachable nodes. Suppose Dijkstra algorithms could be one of the example. Useful in real world navigations, GPS, social networks, if someone asks you, fine. Connected component detections. In undirected graph, BFS can explore and label all nodes in a component. Repeated BFS helps detect disconnected parts of the graph cycles. Whenever you have to, Bellman-Ford algorithm, in Bellman-Ford algorithm, you could use this concept. Cycle detection. In undirected graph, revisit a visited node, not a parent. Cycle exists. In directed graph, BFS in degree tracking, Khan's algorithms helps detect the cycles. So these are the ways where you could use BFS. Yes, you could use DFS also, but in some cases, using BFS is much more convenient than using BFS, right? So I have given some of the examples here, like using level order traversal in trees or graphs, like printing trees, etc. Bipartite graph is the common example of using BFS, and minimum moves in games like chess games and snake ladders. These are the basically practical examples. If someone asks you, serialization, deserialization of trees. Here, basically, we could use DFS also, okay, and BFS also. And since BFS and DFS both concepts can be used in graph as well as in tree, so I've mentioned both here. So I hope you understood the explanation of breadth first search in graph. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's do it by understanding the goal. We are given 2D maze grid of m cross n size, where dot represents an empty cell, plus represents a wall. Okay. We are also given an entrance cell where we start inside the maze. Okay, these are things which we are clear to us. We can move in four direction: up, down, left, right, up. Okay, up, down, left, right. Yeah, but only through the empty cells. Our goal is to find the shortest number of steps to take, which it takes to reach the exit. So if we have to find the shortest, okay, if everyone knows Dijkstra, that's the thing which will come to their mind. But I don't think Dijkstra is needed here. But we know how Dijkstra is coded, right? Which is yes, BFS. An exit is an empty cell located at the border of the maze, excluding the entrance itself, right? We are not allowed to take entrance as the exit, okay? If there is a path from entrance to any border cell, return the number of steps, otherwise we return -1. Which graph traversal will be more intuitive? Let's figure out, which is BFS already, I have said to you, because we have to find the shortest thing here, right? And we have to count for the minimum number of steps. So now, since I have already told that here the keywords are shortest path, right? And finding step by step, right? Because suppose if you're standing here, this is one road, this is another road, there is something in between, landmark is there, right? This is another road, this is another road. So, and you have to reach the shortest, you have to reach the nearest exit from this particular source, right? If you take one step, you reach in this exit, in this you will reach here, and you will reach here, right? But this way is one of the way to understand that, yeah, this proves that using BFS makes much more sense, right? And it is much more intuitive because in the second step you will be here, it will be an exit, but you already got the exit in this particular case, right? Now let's visualize the process here. Imagine a grid where some cells are walls and others are paths, right? Okay, so I've drawn a maze just to visualize the process. Fine. Suppose we start from here. I have already given you gist of why BFS will make sense here. Now let's visualize the process. We're standing here, okay? Now you could go up, left, right, down, and left. Fine. So if you're standing in this particular part, okay? So if you move step one, where you could go? You can come in this particular part, right? You can come here and you can come here. Fine. And suppose you have entered these three values inside the queue. Okay. Suppose let this be, let me mark the edges also, indexes also. Okay, so you have put basically 2 comma 1 you have entered 1 comma 2 also, and you have entered 2 comma 3, and this is at level 1. Okay, so you have counted one step or the level. Fine, step is equivalent to the level. Fine. Now, suppose you pop this value since you are using BFS. I'm assuming that you know how BFS work. Okay, as I've already explained before also. Now, when you pop this, you could either go up, which is block, down, which is block. In the left, yes, you can go right. So what you do, you come here, okay, and you enter 2 comma 0 into the queue. Fine. So because of that, since you came in this particular part, 2 comma 0, the step will increase to 2. Okay. Now you will pop 1 comma 2 because it is the next one. You will check, okay, since we cannot go up or left, but you could go right, right? So what you do, you push 1 comma 3 into the queue. Great. And so you are marking it with them visited also, right? I'm not doing that part now. Now from 2 comma 3, okay, you're standing here. You cannot go up because it is already visited. You cannot go to the right because it is a block path, and to the down also you cannot go because it is blocked, and to the left it is the entrance itself, so you cannot go right. So this remains unused. So we will just pop it and nothing will happen there. Okay. So now you have 2 comma 0. Fine. From 2 comma 0, you can clearly see we can go to 1 comma 0 index. Okay, so I posted into the queue and I will pop this. Fine. Then from 1 comma 3, you could see, okay, the step will be increased to 3. Okay, from here you came here 1, this is 2, this is 3, right? Now from 1 comma 3, you can go to 0 comma 3. So you push it into the queue and you will pop this, right? So you could come here. Now, since the level is itself the 3 for this particular thing, you will increase the level, but this 3, right? So nothing to be done. But now if you check, you are at first row, which means you have got the exit. So what we will do, we will return till level of the step, which is 3 for this particular case. And we will end up the for loop there and there, then and there. Fine. So this is what was written here in point-wise way. So I hope you understood this visualization process. It was pretty simple and straightforward. Now how we can simulate this, okay? We treat every empty cell as a node in a grid-based graph, fine. From the entrance, we perform the BFS. We use a queue to store the current cell positions. For each step, try moving in the four directions, up, down, left, and right, fine. So for this, basically, you could give a for loop to go up, down, left, and right, okay? And this will be within the while loop of the queue, while queue is not empty. If the next cell is within bounds and it is not a val and hasn't been visited, we will mark it as visited and change it to plus. Makes sense because suppose instead of using a visited array or list, you could just convert this to a plus, right? So you won't be able to automatically visit this particular part of the grid. Add to the queue and explore the future steps. Fine. At each level, we increment a step counter or the level, which we already did, which we already got explained previously. The moment you encounter an exit, a cell on the boundary that is not the entrance. Also check when you are at the first row, last row, first column, or last row. If the dimensions or the row comma column value is not equal to the entrance dimensions. Fine. The queue is exhausted and no exit is reached, we return -1. Fine. It makes sense because if the queue got exhausted, okay, and you haven't reached any exit till now, that means that there was no exit it's present there. Now, what we figure out? The problem reduces to finding the shortest path to a border cell in a grid while avoiding the ones. Find shortest path, basically this one. BFS is the ideal here since it explores level by level and guarantees the shortest path. Also, let me explain you again. If this is a road given to you, okay, and I ask you, this is the source, please find the nearest exit for me or find the nearest leaf for me. And if you use the BFS, what you will do, you will come from this node to this particular level, right? You will increase the count, okay? Then from here, when you will come to this particular, when you will try to come to this particular node children's or the levels, you will see that, okay, there are no more nodes to it. But to these levels, you will store this value and this value, right? So for this level, there would be a level 2. But for this, there are no more levels, right? So from here, we can understand going stepwise or level wise help us to find the nearest exit. Fine. So we mark visited cells to avoid revisiting and ensure efficient traversal. Instead of marking visited, we are just changing dot to a plus. Okay. As soon as we reach a valid border cell, it is not an entry, we return the number of steps. So I hope you understood the intuition. It is pretty simple and straightforward. Now let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. Step 1. Initialize variables and prepare for BFS traversal. Okay. We are given a 2D grid and a starting point, right? And we determine the size of the grid and prepare BFS directions. Now, here dx, dy for four-way movement, up, right, down, left. Okay. So dx means x-axis, y means y-axis. Okay, let me explain this to you. Suppose this is the part, right? Okay, let this be a y, let this be a x, and this is 0, comma 0. Okay, if we have to go to left, what will happen? This is the row, correct? So row is not changed, but the column has been changed. So you will do -1, right? If you have to go to the top or the up, okay, let me change the color of the pen. If you have to go to up, right, what will happen? The column is not changed, right? But the row has been changed. And since we are going up, we're subtracting the value from the row, correct? Now, if you have to go to the right, row is not changed, but the column value has been increased to 1. Okay, by 1 it will increase every time. Now, if you have to go down, the row will not change, but the column value will increase by 1. Correct? Now, from here, dy becomes this value, this value, this value, Okay, dy will become 0, 1, 0, minus 1. Okay, and dx will become minus 1, 0, 1, and 0. Okay, so this value represents up. Okay, up because x comma y. Okay, this is x comma y. This one. This value represents right, which is 0 comma 1. This value represents down, which is 1 comma 0, x comma y. Correct. This value represents left side, which is x comma y, which is 0 comma minus 1. Correct. This makes us easier for go on a loop to move in all the four directions. And here, if you could see a four-way movement, right? And a queue is initialized with the entrance cell. It is a common practice of BFS. We mark the entrance cell as basically and basically replacing dot with a plus sign. This ensures you don't revisit the cell and avoids infinite loops. Now, step two, to begin level-wise BFS to find the nearest exit. Okay, basically BFS traversal we will do in this particular step. We use BFS to explore the maze level by level, tracking the number of steps taken so far. At each level, we process all cells currently in the queue. Okay, and for every cell we deque, and if it is at the border, that is at the edge of the grid, and it is not an entrance, we return. So how we figure out it is a no the edge? You could say if this is this part of the first row or the first column, first last row, first column, and the last column. How do we figure this out, right? Two, uh, for this to happen, if it is a first row, the row value will be 0, and the column value could be anything from 0 to n. Correct? If it is a row, last row, the value of row would be n, and column would be from 0 to n. Correct? And if it is a first column, row value could be from n 0 to n anything, but the column value should be 0. Similarly, if it is the last column, rows value could be from 0 to n, but the column value has to be n. Correct? This is clear indication for that. Okay. So we could put a case here that if I is 0, basically row is 0, or if j is equals to 0, and or I is equals to n minus 1 or j equals to m minus 1. Okay. If and also check that I maze of ij is not equals to the dimensions of the entrance. So this way we could check for the exit and return the answer there itself. Otherwise, we attempt to move in all four directions from the current cell. Okay. Now explore valid neighboring cells. For each of the four directions, we compute the new cell. Now how we will compute all the four directions, right? That is the important thing. So what we will do, we will run a loop for k in range 4. Fine. Then we will have a new row basically, and new j, new row basically. Fine. Then here we will have I, here we will have j. Okay. And here we will have dx, k, dy, k. These are the list, if you remember, we created beforehand. And dx is basically minus 1, 0, 1, and 0. Correct? Dy is 0, 1, 0, minus 1. So now what happens is that I and j, these are the values which you get from the queue when you pop the value. Okay, dimensions of the particular grid item. Suppose let that be 0 and 0. Okay, let it be 0 and 0. And dx of k, which means if k value is 0, okay, then dx of 0 is what? For this, you have minus 1. For this, you have 0. So what happens? The new row comes out to be minus 1, and the new j still remains there. Fine. Now, when k value becomes 1, you will take 0 and 1 from this particular list, right? So this becomes 0 and this becomes 1. So new directions become 0, comma 1. Correct? Then the k value becomes 2. So you take values 1 and 0 from here and you update it. So it becomes 1 and this becomes 0. So you get new output as 1 and 0. Then the k value becomes 3. So you take 0 and you take minus 1. So the new output becomes 0, comma, minus 1. So these are the four directions which are basically up, right, down, and left. Fine. So check if it is within the bounds and not a wall. Okay. So basically, when we get this uh, points, rows and column, we will check if it is a plus or dot. If it is a dot, well and good, we will move to that particular thing and we will push it into the queue. If it is not, we won't do anything. Okay. And secondly, we will also check that we are not going out of bounds. Suppose you're standing here and you're looking outside of the grid. So you have to check for that. Basically, the check will be done by using the following condition, like if I is greater than or equals to 0 and I is less than m or n, whatever the value, let it be n here, okay, not n. Similarly, if j is greater than or equals to 0 and j is less than m, okay, if this condition satisfies, then and only we will move ahead. Fine. This ensures you only explore reachable paths and prevents revisiting the same node. Okay. Now in step 4, we track the labels to represent the steps. After processing all current cells in the queue, that is level 1, we increment the level counter. So suppose one level is done. Now when we move to level 2, we increment the count in that case. That is a simple thing so far. And at the end, after the complete traversal is done, if we reach a border cell during traversal, we return the current level immediately, right? Like queue is not emptied or we have not explored all the grid columns or row columns basically. And if we find the exit in between, okay, our traversal, then we will return it immediately. Fine. And if we don't get it and all the traversal is complete, then we will return -1. Therefore, there is no exit for the particular grid. Okay. So I hope you understood the approach explanation. Now let's move to the next slide. Now the code is the exact copy of the approach we discussed. Let's understand it line by line. So this is the rows and columns which we have taken out. These are the directions which I mentioned earlier for the four-way movement. This is the queue. We append the entrance 0, 1, basically 0, 1 means the dimensions, right? Row and column. We need both. We make that particular maze entrance to be positive. Instead of creating a new visited array, we are just modifying the given grid to us. The level starts with a 0. We take the size of the particular level. Okay. We go for the range. We pop the values I and j row column. We check if the ij is not equals to the entrance, and secondly, either of the value is either in the first row or first column, last row or the last column. Right? If it is there, then we just return the level immediately. No need to go anymore. Otherwise, you go to the four directions which I showed you earlier in the visualization. Which I showed you earlier. Okay, and we check for the condition if it is not in the out of bound. First thing, and secondly, can we move to the particular grid or not? Okay, and then we mark it to plus means it is visited. Then we append it to the queue, and then after that we increase the level 1 after completing the complete level. Okay. Now for this particular code, time complexity is n cross n. It's simple as that because you are using a grid, and there are n rows, m columns, m rows and n columns, and we are traversing for each row n number of times the columns, and vice versa. And space complexity is m cross n because we are using a queue here, and that occupies that particular space. Now the space complexity is m cross n. Reason being, the queue can hold up to m cross n elements, right? In the worst case scenario, if the entire maze is empty and no separate widget matrix is used, so therefore no need to count for that particular thing. Therefore, here is the queue is only using the maximum space, which could be m cross n, and this uses constant space, so no need to count for that. And the time complexity is m cross n, as I already explained, because it is a grid. And in the worst case, we might visit all the particular cells, right? So I hope you understood the code explanation along with time and space complexity. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. Let me draw the graph. Let me draw the grid beforehand. Okay, now let's start with the diagram here. So we have n and m already. Okay, so here n is 4 and m is 3. Okay, we have dx and dy fixed with us. Okay, we have the dq. Okay, now we will append values in the q. Fine. So let the q be here. We have appended the entrance value. Entrance value is 1 comma 2. Okay, and after that we have marked it as visited by making it as plus. So 1 comma 2 is this. Okay, level is 0. Now we take the length of the particular level, which is 1 in this case. Now we pop the values, which is 1 comma 2 here. Okay, this is popped. Now we check if 1 comma 2 is not equals to the dimensions of the entrance cell. It is equal, right? So this condition becomes false. Now we come to the for loop part here. Now this is I've written already here. Now I is 1 here and j is 2 here. And this goes from 0 to 3. I hope you understood this thing. Now when dx and dy, which is here, right? So when we have dx k value 0, then we will put here minus 1 and 0. So our cell icons become basically the value becomes 0 comma 2. Now 0 comma 2 here is this 0 row and second column, this one, right? We will check, is it within the boundation? Yes, it is within the boundation. Is it equal to the dot? Yes, it is equal to the dot. So what we will do, we will make it as plus. Okay, we'll mark it as plus since it is visited, and we will append it to the queue 0 comma 2. Fine. After that, k value increases from 0 to 1. Fine. So this is done. In 1, we have 0 comma 1, 0 and 1, right? So the new dimensions becomes 1 comma 3. 1 comma 3, we have a plus sign. Okay. So this thing never happens because it is not a dot, right? So we cannot go there. Okay. Then when k value becomes 2, it is 1 comma 0. Now k value is 2. Okay. So it is 1 and 0. So the new direction becomes 2 comma 2. 2 comma 2 is basically this part, right? And since this is plus already, it will check is it equals to dot? No, it is not. So we cannot go there. So we move ahead. Now here, k value becomes 3 finally. So when k equals to 3, then dx of 3 is 0 and dy of 3 is minus 1. So 1 plus 0 gives me 1 and 2 plus minus 1 gives me 1. Okay. So this is what the new part is here, right? So we check it is within the boundation. Yes, it is within the boundation. Is it equals to the dot? Yes. 1 comma 1. Yeah. So what happens? We mark this as visited. We append it to the queue. Okay. Fine. Which means that our level 1 is complete. Now this is level 2. No. Okay. So what happens? We increase the level plus 1. So our level value becomes 1 because we already completed this level 1, right? Now we are entering the level 2. Therefore, we increment the level value to 1. Now, when we go back, we take the length. Now it is 2, right? We pop the value. We pop this basically. I will write here itself directly. We will check if 0 comma 2 is it equals to the entrance dimensions? No, it is not. Is I equals to 0? Yes, I is equals to 0. Also, if you could see, j is also equals to 0, right? Which means that we are already at a edge of the grid, which is the first row here, this one. Therefore, we return the level. Since level value was 1, it will return 1. Okay. And therefore, the output for this particular question is 1. So this way, the complete dry run is completed, and this way the BFS traversal is used here. So I hope you understood this complete dry run. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach and the code, and also the BFS concept if you don't know. After that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Let's start by taking the dimensions here. So this is the row value basically, fine. So row is n, column is n, Let's create this directions -1, 0, 1, 0, and for the y axis 0, comma 1, comma 0, comma -1. We'll create a queue here using Deque. We'll append the entrance values. Okay. After that, we will update the maze also. We will do like we'll take this. Okay. Basically this way. Okay. We'll mark it as plus. Further, we'll take a level, initialize it 0. While queue is not empty, we will take the size of the particular level of the queue. Okay. For in range the size ij q dot pop left if I comma j is not equals to the entrance and I equals to 0 or j equals to 0 or I equals to n minus 1 or j equals to n minus 1. This is basically we're checking for the edge of the grid. Okay. If it is true, we return the level immediately that we have found the exit. Otherwise, we go for the four directions for a in range of 4 new row is basically one I plus bx of I new j equals to j plus by of k, not I, sorry, k. And after that, we'll check for the boundation. If the new I value is within the range, okay? Mu of I, if it is less than, greater than equals to 0 and less than n, and similarly for the column also, and also the maze value for this new shell equals to a dot, which means we can access it. If it is, what we do, we take maze, we simply take this, okay, paste it here, and we'll remove this, take this, paste it here, take this, put it here, and we'll say mark it as plus. Means we have marked it as blocked or visited. Then we append it to the queue. Okay, and then after this traversal is done for this particular level, we increase the level by 1 and we return -1 at the end. Now let's try submitting this for the sample test cases. Okay, now finally submit the solution. Okay, so we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.